Some people deserve fudge. That's right, today we're talking about the modern model of the atom. Hit the theme.
Ain't nothing but a chem thing, baby. Two flipped out teachers going crazy. Lancaster is a district that pays me. Unbreakable, so please don't try to break this. But back to the lecture at hand.
Hello and welcome to another episode of SchuFu Chemin at ya. I'm your host Shu, and with me as always is Fu.
What up, nerds?
So Fu, it's been a long journey, but we've finally arrived at the last episode in the atomic theory unit.
Yeah, we're going to revisit that modern model of the atom again, which is a little more complex than the Bohr model, but we're really going to focus in on those electrons. So let's get started. Atomic Skills Part 4, the modern model. A lesson from the atomic theory unit. How to describe an electron. In the modern model, it is too simple to describe an electron by its energy level only. There are 4 subdivisions that allow us to zoom in on a single electron.
So you're a student at Lancaster High School. Let's use a little analogy here. You're an electron, and Lancaster High School is the atom. We want to describe where you are. Well, in the Bohr model, we're not very descriptive. We're just looking at the energy level. So that would be like describing you as being in freshman, sophomore, junior, senior hallway. We have some idea of where you are, but it's not very specific. Well, in the modern model, we want to be more specific. So we want to describe which exact classroom you're in and which exact seat you're sitting in within the classroom. Let's begin with the first subdivision, principal energy level given the letter N. The higher the integer value of N, the higher the energy and the farther away from the nucleus. So for example, N equals 3 would be the third energy level.
So principal energy level is as specific as the Bohr model gets. So again, to tie it back to our analogy, this is kind of like telling which hallway you're in at Lancaster High School. So our next subdivision is called the sublevel. There are locations within an energy level that have different general shapes. We specify these using different letters. S, which has a spherical shape, P, which has a dumbbell shape, D, which has a 4-leaf clover shape, and F, which has a 4-leaf clover on crack shape. Now to remember S, P, D, and F, some people deserve fudge. It's a great way to remember.
To continue our student analogy, we already know which hallway you're in, that's the energy level. Now with the sublevel, we're specifying the classroom within that hallway. Our next subdivision is the orbital. Within each sublevel, there are different orientations of the electron clouds in space. Now when we say orientations, we're talking about the electron clouds in 3D, oriented along the X, Y, and Z axes. Each sublevel has a certain number of allowed orientations, also known as orbitals, a term you've heard before.
Yeah, I remember that.
So if you remember our sublevels from before, we have S, P, D, and F. And within each of those sublevels, there's a certain number of orientations or orbitals that are allowed. So for example, in the S sublevel, there's 1 orbital allowed that is shown at the top of the picture. In the P sublevel, there are 3 orbitals allowed. That's shown in the middle of the picture. The D sublevel is allowed to have 5 different orbitals, also shown in the picture at the bottom. And F gets 7 orbitals, that's not shown in the picture. These are easy to remember because they are just the odd numbers, 1, 3, 5, and 7.
So to tie this subdivision into our analogy, we already know what hall you're in, that's the energy level. We know what classroom you're in, that's the sublevel. The orbital would be analogous to the desk you're sitting at in that classroom. And our final subdivision here is the electron spin. So each orbital can hold 2 electrons, no more. The spin specifies which electron within the orbital we are describing. So we have something called the Pauli exclusion principle, that no 2 electrons can have the exact same 4 subdivisions. So at least the spin has to be different.
So in our student analogy, we already know the hallway that you're in, we know the classroom you're in, and we know where you're sitting. Let's say instead of a desk now, we're at a lab bench. We can fit 2 people at this lab bench. You're sitting on one side, another student, your lab partner, is sitting on the other. So you're in the same hallway, classroom, and lab bench. So 3 of those 4 subdivisions are the same. But that last one, the spin, has to be different, and that is shown by you sitting on opposite sides of that lab bench. Let's continue by talking about electron configurations with sublevels. An electron configuration represents the correct number of electrons in the appropriate energy level and sublevel. So this is more detailed than a Bohr electron configuration, which only said the number of electrons total in each energy level. You should begin at the first element on the periodic table, which is hydrogen. You're then going to proceed from element to element, going left to right and top to bottom. As you do this, you add electrons to each energy level and sublevel as superscripts until you reach the desired element.
So if you take a look at our example down here, we have 1s1. So let's break that down. The big number 1 in the front, now that represents the principal energy level, just like the Bohr diagram was the first energy level. The S represents our sublevel, and the superscript of 1 tells us how many electrons are in that particular sublevel. Every row or period represents N, which is the energy level being filled. The periodic table is also arranged into different blocks that represent the sublevel being filled. The first 2 columns are the S block. The last 6 columns are the P block. The middle 10 columns are the D block. And that bottom 14 columns there, that's the F block.
I'd like you to take out your periodic tables. We're going to do some labeling. No, really, take out your periodic tables. I want you to label them. It's really going to help a little bit later. Okay, we're going to label our sublevel blocks. So let's start out with hydrogen and helium. These are both part of the S block. So label S's above both of those elements. The first 2 columns on our periodic table, called groups, are also part of the S block. Continuing on, let's look at the P block. The P block is the last 6 columns. So just above those 6 groups, label P. We're always filling up the P sublevel here. Continuing on, let's take a look at groups 3 through 12. This is called the D block. And finally, the very bottom, this is the F block. In general, the higher the energy level, the higher the energy. Exceptions: D sublevels are always 1 energy level below the one you are filling up, and F sublevels are always 2 energy levels below the one you are filling up.
So to illustrate this better, take a look at the diagram that's on the screen here. So we have the 4th energy level starting in that 4th row, where the 4s is. So we fill in that 4s first, then we actually go down an energy level to the 3 to get to the 3d. Now we fill in the entire 3d, and then we hit the 4p, where we go back up an energy level. So that d is always 1 energy level below. If we take a look at the 6th energy level, which is the 6th row down in the S block, the 6s, we fill in the 6s, and then we hit the 4f. So we go 2 energy levels below to hit that F block. And then we will go back up to the 5d, fill that in, and then we will hit the 6p after that.
We're going to do some examples to practice electron configurations with sublevels. Remember, those are different from Bohr electron configurations. Are you ready, Fu?
I am.
All right, let's get started. Let's take a look at carbon. We're going to write its electron configuration with sublevels. So Fu, first thing, let's find carbon on our periodic table.
All right, carbon's element is C, so it's right there on our periodic table.
All right, now what we're going to do is we're going to kind of count over from left to right and top to bottom, filling up electrons until we get to carbon. So actually, we're going to start at hydrogen, like we're filling up that first electron. So go to hydrogen.
It's right here.
And what energy level are we in right now?
We are in the 1st energy level, that 1.
Good, that 1, that row means we're filling up the 1st energy level. Now, what block are we in terms of sublevel?
Well, the first one there is the S block.
Good, we're in the S block, so we're filling up the S sublevel. And we're going to kind of count over and fill up that whole sublevel. Helium is a part of that S block as well. We're counting over.
Okay, so we're going to fill in hydrogen and helium. So that was 2 electrons.
2 electrons, good.
So just to recap here, we are in the first energy level, so 1 is the first number.
Good.
We're in the S sublevel, so S is our sublevel. And there were 2 electrons, right, for hydrogen and helium, so the superscript is 2 for both those electrons.
Very good. 1s2 so far. We filled up the first energy level. Let's move on now to the next element in the second energy level.
All right, so that next element is lithium after helium, and that is in that second energy level.
Good. Now what block are we in again?
We're still in the S.
Good. So let's fill up the S now, counting over.
All right, so lithium and beryllium fill that out. So we are in the second energy level. We're still in the S block, and we just had 2 X's for 2 elements, so that's 2 electrons.
All right, very good. Now we're still in that second row, but we kind of jump over.
Oh yeah, look at that.
All right, so what block are we in now?
So this one over here is that P block.
Very good. All right, so still second energy level, but now the P block.
Okay, and it looks like we've got 2 elements before I get to carbon.
Right, we want to make sure we stop at the desired element. We don't want to keep counting to fill it all up.
All right, so we're in that second energy level still, so 2. We're in the P block, so P, and it was 2 X's, 2 elements, that's 2 electrons. So
Very good.
1s2, 2s2, 2p2.
Well done. All right, we're going to try a slightly more challenging one. This is scandium. So let's find scandium on our periodic table.
All right, so scandium is Sc, and that is right there. All right, that's a little further down.
Yeah, we're going to have a few more electrons to fill up. All right, I'm going to let you take the lead here, though, since we've done one. I'll let you start at the beginning and kind of count over.
All right, so we're always starting at hydrogen here. That's in my first energy level, and I've got 2 of those there from my S block, so that's a 1s2. It sounds familiar.
I was going to say there's going to be some repetition with these as you keep doing them.
And then I hit my second energy level there with lithium and then beryllium. So again, that's in the S block, and I've got 2 electrons there, so 2s2, just like before.
Very good.
Oh, yep, so we gotta skip all the way over here, and I gotta fill in all these, right?
Yes, you do.
All right, so that is 6 X's, 6 elements, so is that 2p6?
Very good. We filled up the 2p sublevel.
All right, so then after neon is sodium down here, Na, right? So that's in the third energy level, so is it 3s?
Yep, 3s. Fill it up.
And crossing both those out gives me 2.
Good.
I'm guessing I'm skipping over again, right?
Mm-hmm.
All right, so now we're still in the third energy level?
Still in the third energy level.
Okay,
Good.
and okay, this is the P block again, and I've got 6 electrons.
I think you're noticing some of the patterns
Yeah. All right. After argon is potassium over here. That's in the fourth energy level. So 4, back to the S block, 4s.
here. Yep.
And there are 2, so 4s2.
Good. Now, let's take a look at this next section. This is a little bit different. What block are we going to be in?
We're in the D block.
Okay, good. Now, there's a special rule about the D block. Do you remember what that was?
Oh, it's always 1 energy below.
Good. So we started filling up the fourth energy level. We're actually going to go back and fill up some more of the third that's left
Okay,
over.
so even though this is in the 4th row, that means the D is actually in the 3rd energy level?
Very good.
Okay,
yes.
so then this isn't 4D, this is 3D.
3D. Good.
3D, and well, scandium's the first one, so just 1.
Just 1 extra electron there. Very good.
All right, I think I got it.
You try number 1. You're going to write an electron configuration with sublevels for germanium. Be sure to use your periodic tables and count over.
An abbreviated electron configuration uses the group 18 element filled last, written in brackets followed by the remaining configuration.
Let's take a look at the electron configurations that are listed in the picture. We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. And it turns out that 1s2, 2s2, 2p6, 3s2, 3p6, that section of it, is actually the electron configuration for argon. So instead of writing that all out, we condense it down to argon in brackets, and we leave the remaining part, 4s2, 3d6, intact.
All right, so we're gonna do some examples of some abbreviated electron configurations with sublevels here. Shu, are you ready?
I'm ready.
All right. Carbon. All right, so on our periodic tables, where is carbon?
Carbon is right here.
Good. Now, in abbreviated versions, we use the electron configuration of the previous group 18 elements just in brackets. So, which group 18 element comes before carbon's atomic number of 6?
If I kind of move back, it looks like it's going to be helium.
All right, so we're going to abbreviate that simply with helium in brackets, He in brackets. Let's get that down.
All right.
Okay, so unlike having to start from hydrogen every single time, we can start from the next element that comes right after that group 18 element.
All right, so that would be lithium right here.
Good. So what energy level are we in here?
We are in the second energy level.
Good. What block are we in?
We are in the S block.
Good. So we're in the S sublevel, and let's fill that in.
All right, so we go over 2 elements to fill up that block, so 2s2.
Perfect. All right, so remember, we got to skip over this gap here, right?
All right.
All right, so what energy level are we in?
We are still in the second.
Good. What block are we in now?
We are in P now.
Okay, so let's fill that in.
All right, got the P. So just want to count over. 1, 2.
Good, making sure, again, we're stopping at that element and writing those electrons in.
So it's really similar to what you did. I just had a little less to write because I got to put helium there instead of the 1s2 thing.
Yeah. All right, so I remember scandium was a pretty long one when I did the example. So let's see how this one changes. So where is scandium on the periodic table?
Got it.
And what is the group 18 element that comes before scandium's atomic number?
Just kind of going back. It's argon.
Good, so we're going to write argon in brackets, and I'm going to let you take it from here.
Hey, there's a lot I don't have to write. There's 3 whole rows all done with argon in brackets. Cool. So I'm going to move down to the 4th energy level. I'm going to start at K. So 4 for 4th energy level. I'm in the S block now. I'm going to count over 2 elements. So 4s2. And then over here, I know I'm in the D block, but the rule is that I've got to go back 1 energy level. So I know that's 3D, and it's just 1 electron for 3D.
Good, much shorter. You try number 2. Complete the abbreviated electron configuration with sublevels for germanium.
Orbital diagrams. Orbital diagrams represent the actual electrons as they reside in their orbitals with their separate spins. No, this has nothing to do with a Bohr diagram. You're going to use your electron configuration with sublevels that we just worked on. Note the number of orbitals in each sublevel. Remember, S has 1 orbital, P has 3, D has 5, and F has 7, 1, 3, 5, 7. Each orbital contains 2 electrons, and there's a very special rule called Hund's rule. You're going to always leave electrons unpaired before paired within a sublevel.
So we don't mean to sound like we're venting here, but this really is our first source of frustration with us chemistry teachers and you guys as the students. Students tend to mix up and they confuse orbital diagrams and Bohr diagrams.
So just to clarify, in a Bohr diagram, we've got our nucleus and we've got our electrons filling up the shells as represented by arcs.
Yeah, and in orbital diagrams, it's a lot more inclusive with the electrons in orbitals. They're in boxes, you're filling them in with arrows. There's a lot more to it. You have to use the electron configuration with sublevels, even just to draw out the orbital diagrams.
Let's do some examples. We're gonna practice drawing some orbital diagrams. So you ready, Fu?
I am.
All right, we're gonna begin with helium. We always wanna start with the electron configuration with sublevels. So what is that for helium?
That is 1s2.
Very good. We're gonna focus in on the sublevel, the S sublevel. How many orbitals should the S sublevel have?
Well, SPDF has 1, 3, 5, 7, right? So S has 1.
All right, good. So 1 orbital means we're gonna drop 1 box to represent that orbital.
Got it.
All right. Now, we have 2 electrons as denoted by the superscript in our electron configuration. So how are we gonna fill up 2 electrons in this orbital?
Gonna draw 2 arrows.
You have the right idea, but we do have to go back to that electron spin concept.
Oh.
So if we're in the same orbital, 2 electrons actually have to have opposite spins. So we're gonna represent them with an up arrow and a down arrow.
Gotcha, all right, good.
That's it for the orbital diagram of helium. All right, now there's something I kind of wanted to point out. I want to tie this back to some of the skills we talked about in the previous lesson.
Okay.
Let's talk about Lewis dot diagrams. So how many valence electrons do we have here?
All right, so, well, there's just the 2 electrons there, so 2.
Good, so let's draw a Lewis dot diagram for helium then.
All right, so helium, the Lewis dot, we always start with the symbol, right?
Mm-hmm.
And then those first 2 electrons always got paired up, right?
Good.
Like 1, 2.
And actually that's why I'm bringing this up right now. Do you see how we have 2 electrons paired up in that one orbital?
Oh,
That's why we
okay.
pair them up in our Lewis dot diagram.
Makes sense.
All right, good. Let's move on to fluorine number 2. Let's get that electron configuration with sublevels again.
So fluorine is 1s2, 2s2, 2p5.
All right, so it looks like we've got 1s2, 2s2, both with s sublevels. So that means how many boxes should we draw for each of those?
So each one gets 1, right? Because those are s sublevels, they got 1 orbital.
Good. And what about for the p sublevel?
All right, so it's sp, df, 1, 3, 5, 7, p is 3.
All right, so we're gonna have 3 boxes to represent the 3 orbitals in the p sublevel.
Okay.
All right, let's label those below.
1s, 2s, and 2p.
Right, all 3 of those boxes go with 2p, very good. Now we're gonna fill in our electrons.
All right, so they gotta have opposite spins, right?
Very good.
Up, down, up, down, up, down, up,
Whoa.
What?
There's actually another little trick here, that's Hund's rule. If we're in the same sublevel, you actually want to keep them all unpaired in separate boxes before you pair them up.
I remember. Okay, so I'll put single arrows in first.
Good.
That's 3, and I need to get 5, so I need 2 more, right? So I can pair them back up.
Good. Now to really kind of bring everything together, let's do a Lewis dot diagram. How many valence electrons do we have here?
So valence electrons are the ones in the outermost energy level, and that would be the 2 here. So it's all of these electrons, right?
Good. Don't just look at the last number and think that it's 5 because we have the S and P sublevel in that second energy level.
Okay, so there's 7 valence electrons?
Good, we have 7. So when we do this Lewis dot diagram, let's show that special filling rule that we had for Lewis dot diagrams and tie it to the orbital diagram.
All right, so the first 2 go on top, and then the Lewis says we go around the horn here, right, in a clockwise motion until we get to 7.
Good. Now do you see how you paired up those 2 at the top? That was filling up the 2s.
Oh, gotcha.
And then when we did our 5 electrons, remember we made that little mistake with Hund's rule being forgotten?
Oh, that's right.
So we did unpaired, and then we came back around and we paired up. And that was the way we have to fill up the 2p sublevel.
So it's almost like those are the boxes.
Exactly, very good.
Nice.
All right, last one, number 3, manganese.
Okay, so that's pretty long. Can I shorten that?
All right, yeah, let's do an abbreviated.
All right, so argon is the group 18 element that comes before, so I'm gonna put that in brackets, and then from there on it's 4s2, 3d5.
Good. So again, for our S sublevel, how many boxes will we draw?
That would be 1.
Good. Now what about for the D sublevel?
Okay, we finally had 5.
Okay,
So 5 boxes, that's pretty long.
it is. Okay, let's label those.
Okay, so, this is the 4s then.
Yep.
So I can leave all that other stuff off that would have been before here?
Yeah, since we wrote an abbreviated electron configuration with sublevels, we'll do the same for our orbital diagram.
Nice, that really shortens it up. So this is 3D then.
Yep. All right, let's fill in our electrons. We've got 2 for the 4s.
All right, I think I got this. So they get paired up, 1, 2, and then these guys got to go in single, right?
Very good.
1, 2, 3, 4, 5. So they're all single.
Very good. You try number 3. You're going to write an abbreviated electron configuration and draw an orbital diagram for tin. Now a little bit of a hint, you may want to use table S to look up the element symbol.
It's not TI.
Let's take a look at some different visual representations of how electrons are filled up in the atom. If we look at the picture on the left, we see our energy levels going 1 through 5 from bottom to top. We're moving away from the nucleus, and we see the order that the sublevels are filled in. So 1s, 2s, 2p, 3s, 3p, and then if you remember, 4s comes before 3d, and this is a nice visual representation in terms of energy. Even though D is a part of the third energy level, it's slightly higher in energy than 4s. That's why we fill up the 4s first. If we look at the picture on the right, we see the same order of filling, but now we see all the boxes that we need to fill. Similarly, if we look at the orbital stairs, they kind of progress from left to right, low to high energy as we move from bottom to top, representing all of the orbitals as lines. That's going to do it for today's episode on the modern model of the atom.
Later, nerds!
Today's episode is brought to you by
Lindsay's Hot Ham Water. It's watery, and yet there's a smack of ham to it. Just add water.
But we never off, always on till the break of dawn. SCIENCE in the hall they call S-Wing. You know we never wear a tie like my homies, boys to men. It's so hard to say goodbye.
Like this, that, and this, and it's like that, and like this, and like that, and it's like this.
You're going in low power mode.
Plug and chill to the next episode.